Hi, my name is Adam Jones-Delcourt, and this is a brief talk on reverberation and mirror image artifacts in ultrasound. By the end of this session, you should be able to define the term artifact as it applies to radiology. You should be able to identify reverberation artifacts, including A-lines, comet tails, and ring down artifact. You should be able to identify mirror image and multipath artifacts. And you should be able to explain the underlying sonographic principles that cause each type of artifact. So the term artifact in this case actually comes from the root word of artificial. So in radiology, an artifact is something that you see on the image that isn't actually present in reality. And in this presentation, we're going to talk about a couple of different artifacts. We're going to talk about reverberation, which is going to include comet tails and ring down artifact. And we're also going to talk about mirror image artifacts and multipath artifacts. So let's start with reverberation. Reverberation occurs when the ultrasound beam encounters two highly reflective surfaces that are lying side by side in parallel. The beam sort of bounces back and forth a few times between those two surfaces, and that's basically what the word reverberate means, just bouncing back and forth. The most common example of this is something you're probably already familiar with if you're watching this presentation, and that's A-lines. So A-lines are something we see in lung ultrasound, and you see a couple of them in this picture here. Just to orient you to that diagram, the rib is this bright white line up here with a dark shadow behind it. The pleural line is this white line over here. And you imagine the probe sort of sitting up against this skin, kind of out of screen up at the top. A-lines are these white lines down here that are below that pleural line. So how are those A-lines produced? Well, usually the way an ultrasound machine works is the probe fires out a beam, which then bounces off of some kind of structure like the pleura before it comes back to the probe to be registered and measured. And specifically, the machine measures about how long it took for that signal to go out and come back to decide about where and how deep it's going to draw the structure. Now, occasionally what will happen is the beam will bounce off the probe, and then it'll go back to the pleura for a second trip. It then bounces off the pleura a second time and then comes back to the probe. And the machine notices that that beam actually took like a really long time to return. So it assumes that there's another pleural line deeper into the far field, and it draws one somewhere around there. And that's not real. That's a separate artifact that we would call an A-line. Now that process can continue happening again and again and again for as long as that beam has some energy left to it. And each time it returns to the probe from bouncing off the pleural line, the machine will draw another A-line. So an A-line gets drawn for every single trip that beam takes. You can sort of think of A-lines and reverberation in general as what would happen to your voice if you were standing on a mountaintop and yelling into a canyon. So your voice goes out and it bounces off the mountains in front of you and comes back to you, so you hear an echo. And maybe it bounces off of you again and then heads out into the mountains, bounces off the mountains and comes back to you for another trip, so you hear your voice again. And each time it gets sort of faded and faded and faded until it just disappears and goes away. It's the same kind of phenomena here producing A-lines. So that's A-lines and reverberation in a nutshell. The next thing we'll talk about are comet tails, which is a variation on that same thing. Comet tails are just a reverberation artifact that occur when the two surfaces are so close together that you just can't see them or individual A-lines getting produced. So comet tails look like this. So in lung ultrasound, a comet tail would be that little flash just coming off of the pleural line there. Usually a little bit easier to appreciate when things are animated and moving, so you can see it kind of swaying back and forth with a bit of lung sliding. So if you were to take that picture and you were to just blow it up to like a really, really good resolution so you could see everything that was really happening on a microscopic level, you'd probably see something that looks like this. So you have two parallel layers, and maybe this one up here is the parietal pleura, and this one down here is the visceral pleura, those two layers that you see in lung sliding. And when an ultrasound beam hits those layers, some of it just gets stuck and kind of reverberates in between those two layers. So the result are these tiny, tiny, tiny little A-lines that are just so small and so close together that you really can't see them. Now, comet tails are actually not unique to lung ultrasound, though that's probably the only time anybody doing POCUS ever seems to talk about them. Comet tails are actually a technical term in radiology, and you can see comet tails in a variety of different places in somebody's body. So a common example of that would be in the gallbladder. In this picture, you can see in the near field, just along the gallbladder wall, there's a sort of fuzzy artifact which looks like a comet tail. And that's probably produced because the gallbladder's wall is just a little bit thicker with some cholesterol deposition. Another common spot is in the thyroid. So sometimes thyroid cysts will have little bits of calcification in them. And those calcifications are just thick enough that it produces two reflective surfaces and you get this little comet tail following after it. The next artifact that we'll talk about is the ring down artifact, which is usually classified as a reverberation artifact, which occurs at the interface of air and fluid. So ring down artifact is something that you really need to know about if you're going to do any kind of lung ultrasound, because often it's the artifact that helps you declare a positive finding. And if you look at this picture on the left here, you can see some lung ultrasound with a pleural line at the top and these bright B lines that shoot all the way down to the bottom of the screen. We associate this finding most commonly with pulmonary edema, and pulmonary edema by definition is an interface of gas and fluid. So the B lines that get produced here are actually a ring down artifact. It's just what we call them when we see it in the lung. Now, obviously this isn't the only place that you would see. Ring down artifact you can sometimes see in bowel. So on this picture on the right, you can see a small section of small intestine with what looks like some B lines sort of shooting through it. Except they're not called B lines here because they're not in the lung. We would just call this ring down artifact. And again, it's produced by the gas in the bowel mixing with the fluid in the bowel and creating a funky sound wave that gives you this picture. So what's going on here? How do you get this ring down artifact? Well, the mechanism is actually debated and nobody really knows exactly how this works. But we think this happens when air bubbles arrange around fluid in an upside down pyramid kind of shape. So a lot of textbooks talk about an inverted tetrahedron. And it looks kind of like that, or you can imagine it this way, with 3 gas bubbles sorted as a base with one kind of plugged onto the bottom there. And if you have a droplet of fluid in the middle of those gas bubbles, it kind of gets squished into sort of the shape of like a horn, or some textbooks describe like a bugle. And air surrounds that fluid on every side except for the opening at the top. So on the left, on the right, on the bottom, but not the top. And again, nobody knows exactly how this works, but some authors describe this sound entering the fluid and then bouncing off of the gas bubbles a whole bunch of times before it actually escapes. So if this is my fluid droplet, kind of shaped like a horn, the ultrasound beam enters and then reverberates a whole bunch of times before it can escape. And some people think that's what produces the ring down artifact. What you're seeing is a whole bunch of little reverberation lines, much like a comet tail, just a whole lot more intense because it's inside a fluid droplet. Now, other authors think that this doesn't really have anything to do with reverberation and that it's more of a resonant phenomena. So some people suggest that the sound waves hit a particular frequency, which causes a resonant vibration in the fluid. The theory here being that the sound waves enters and the fluid just sort of shakes and vibrates. That vibrating fluid sends out a continuous signal, or almost like a ringing, back to the probe, and that's what you're seeing as this continuous line that never ends. You can almost think of this as like a bell that gets hit with a hammer. For as long as that bell is vibrating, it's emitting some kind of signal. And a B line is basically the visualization of that constant ringing sound. So that covers reverberation artifacts. The next thing we'll talk about is mirror and multipath artifacts, which are artifacts that occur when the machine draws a false image because the ultrasound beam got reflected off of its expected course. Sort of difficult to describe in words, but this is one of those things that once you've seen an example, it's very clear. So every textbook ever, if you look up mirror artifact, will show you this example where you see a bit of liver on both sides of the diaphragm. So just to orient you to this picture, everything up here is liver. Your diaphragm is that bright white line down there. And here you can actually see that there's a little nodule kind of in the liver, just that little sort of hyperechoic spot. Not quite as bright as the diaphragm, but a little bit brighter than the liver. And if you look beyond the diaphragm, you can see maybe more liver down there, and you can see what looks like almost like another nodule. But we know that there's only supposed to be air in the lungs, so there shouldn't really be anything past the diaphragm. So what's happening here? Well, usually, again, the way an ultrasound works is the beam hits something, it bounces back up, and it returns directly to the probe. So it either hits the diaphragm or it hits that nodule, and that's how the machine knows to draw what it's supposed to be drawing and where. But sometimes the beam will come down and it'll reflect off in a completely different direction that the machine wasn't expecting. And usually those signals are just sort of lost. We just don't know what happens to those, and it doesn't really register with the machine. But mirroring will happen when that beam hits something along the way. So if it bounces off the diaphragm and it hits this liver nodule, sometimes it'll bounce back off the nodule, back to the diaphragm, and then return all the way back up to the probe. So it'll do something like that. Now the machine will notice that that beam took a really long time to return. And because it's kind of a dumb machine, it just assumes that it took longer because the thing it hit was deeper and not off to the side or reflected in some other way. So it assumes that there's another nodule somewhere deep and it draws one down there on the other side of the diaphragm. Now it's important to note that that beam doesn't have to return exactly along the same path. So if the beam comes down, bounces off the diaphragm, and hits that nodule, it doesn't necessarily have to go back to the diaphragm before returning to the probe. It could just bounce off the nodule and go straight back up. That's probably going to give you almost the exact same image in this particular case, but because it's a slightly different mechanism, we would call that a multipath artifact rather than a mirroring artifact. Practically, you can't really know which one it is, but there's two different things that could be going on with a picture like this. So just to show you those two side by side, mirror artifact occurs when the ultrasound beam gets diverted, but then returns back along almost the exact same path. So in this example, going from probe to diaphragm to nodule, and then back from nodule to diaphragm to probe. Multipath artifact gives you a very, very similar picture, but the beam is diverted and then returns via a different path. So in this case, going from probe to nodule, up to the diamond, and then back to the probe, rather than going completely reversed along the exact same path. So to summarize everything we've talked about, reverberation occurs when the ultrasound beam bounces between two highly reflective surfaces, kind of like the way your voice bounces around if you were to stand into a canyon and yell out into the mountains. That reverberation is what produces things like A-lines. Comet tails occur when the two surfaces are so close together that you just can't see the individual lines being produced. Think about it as like A-lines but on a microscopic scale. Ring down artifact is a little bit different. It occurs when the ultrasound beam vibrates a droplet of fluid surrounded by gas. Some people think that's a reverberation artifact, and some people think that has more to do with resonance, but nobody's really sure. Mirror artifact occurs when the ultrasound beam is diverted, but finds its way back to the probe by returning along the exact same path, just in reverse. And multipath artifact produces a very similar mirror image kind of thing, but that occurs when the beam is diverted and finds its way back to the probe along a completely different path. And that's it. If you have any questions, put them in the comments below or send me an email. We'd love to hear from you.